العالمين.
Been implementing your very own spell checker using some form of hash table. Well, it turns out that in Python, you can solve those same problems, but perhaps a little more readily. In fact, let me go back over here to VS Code. And let me propose that I do the following. Let me go ahead and create a file called dictionary.py. Let me propose that I try to implement, say, problem set 5, our spell checker, in Python instead of C, and achieve ultimately the same kind of behavior whereby I'll be able to spell check a whole bunch of words. So this is jumping the gun a little bit, because you're about to see syntax we'll revisit over the course of today. But for now, I've got a new file called dictionary.py. And let me begin to create some placeholders for functions. We'll see in just a bit that in Python, you can define a function called check. And that check function can take a word as its input. And I'll come back to this in just a moment. In Python, I can define a second function like load, which itself will take a whole dictionary, just like in problem set 5. And I'll go ahead and come back to the implementation of this. Meanwhile, we might similarly implement a function called size, which takes no arguments, but ultimately is going to return the size of my dictionary of words. And then lastly, for consistency with problem set 5, we might define an unload function whose purpose in life is to free any memory that you've been using just to give it back to the computer. Now, odds are whether you're still working on Speller or have finished Speller, like you wrote a decent amount of lines of code. And indeed, it's been, by design, a challenge. But one of the reasons for these higher level languages like Python is that you can stand on the shoulders of programmers before you and solve very common problems much more quickly, so that you can focus on building your new app or your web application or your own project to solve problems of interest to you. So at the risk of crushing some spirits, let me propose that in Python, if you want a dictionary for something like a spell checker, well, that's fine. Go ahead and give yourself a variable like words to store all of those words, and just assign it equal to a dictionary, or dict for short, in Python. That will give you a hash table. Now, it turns out in Speller, recall, you don't need to worry about words and definitions. It's just about spell checking the words. So strictly speaking, we don't need keys and values. We just need keys. So I'm going to save myself a few more keystrokes by just saying that technically in Python, using a set suffices. Again, a set is just a collection of values with no duplicates. But they don't necessarily have keys and values. It's just one or the other. But now that I have, on line 1, I claim the equivalent in Python of a hash table, I can actually do something like this. Here's how I might implement the check function in Python. If the word passed into this function is in my variable called words, well, return true. Else, go ahead and return false. Done. And wait, you're thinking, if anything at all, maybe we want to handle lowercase instead of just uppercase and lowercase. Well, you know what? In Python, if you want to force a whole word to lowercase, you don't have to iterate over it with a loop. You don't have to use any of that C-type functions or anything. Just say word.lower, and that will convert the whole thing to lowercase for parity with the dictionary. All right, how about something like the load function in Python? Well, in Python, you can open files just like in C. For instance, in Python, I might do open the dictionary argument in read mode, just like fopen in Python. I might do something like this. For each line in that file, let me go ahead and add to my words variable that line. And then let me go ahead and close that file. And I think I'm done. I'm just going to go ahead and return true, just because I think I'm already done. Now here too, I could nitpick a little bit. Technically, if I'm reading in every line from the file, every line in the dictionary ends with technically a \n. But there's an easy way to get rid of that, just like you might in C with an alternative syntax. What I'm actually going to do is this. Let me grab from the current line, the current word, by stripping off with reverse strip. rstrip, a function we'll again see, that just gets rid of the trailing new line, the \n at the end of that line. And what I really want to do then is add this word to that dictionary. Meanwhile, if I want to figure out what the size is of my dictionary, well, in C, you're probably writing code to iterate over all of those lines, and you're just going to count them up using a variable. Not so in Python. You can just return the length of those words. And better still, in Python, you don't have to manage your own memory. No more malloc, no more free, no more manual thinking about memory. The language just deals with all of that for you. So you know what? It suffices for me to just return true and claim that unloading is done for me. And that's it. Again, whether you're in the middle of or already finished, this might perhaps suggest some frustration frustration, but also enlightenment in that this is why higher level languages exist. You can build on top of the same principles, the same ideas with which you've been dealing, struggling even this past week, but you can now express yourself all the more succinctly. Like this one line implements a hash table for you. And all of this now just uses that hash table in a simpler way. Any questions now on this? Keeping in mind that the point, nonetheless, of Speller and PSET 5 is to understand what's really going on underneath the hood. And better still, to notice this. This might seem all rather amazing, but let me go ahead and do this. I've actually got a couple of versions of Speller written here. And I've got a version written in C that I won't show the source code for. But I'm going to go ahead and make that version of Speller in C. And I'm going to go ahead here and, let's say, split my window here for just a moment. And I'm going to go into a Python version of Speller, really that I just wrote. And on the left-hand side here, let me go ahead and run Speller, the version I compiled in C, using a big text like the Sherlock Holmes text, which is a whole lot of words in it. And on the right-hand side, let me run Python of speller.py, which is a separate file I wrote in advance, just like we give you speller.c. And I'll similarly run this on the Sherlock Holmes text. And I'm going to do my best to hit enter on the left and the right of my screen at the same time. But we should see, hopefully, the same list of misspelled words and the timings thereof. So here we go on the right. Here we go on the left. All right. Sort of a race to see which one wins here. C is on the left. Python is on the right. OK. Interesting. Hopefully, Python's close behind. Note that some of this is internet delay. And so it might not necessarily be a crazy number of seconds. But the system is indeed using, if we measure at a low level, how much time the CPU spent executing my code. C took a total of 1.64 seconds. That was pretty fast, even though it took a moment more for all of the bytes to come over the internet. The Python version, though, took what? 2.44 seconds. So what might an inference be? I mean, one, maybe I'm just better at programming in C than I am in Python, which is probably not true. But what else might you infer from this example? Should we maybe give up on Python, stick with C? No? So what might be going on here? Like, why is the Python version that I claim is correct, and I think the numbers all line up, just not the times, where's the trade-off here? Well, here again is sort of this design trade-off. Yeah? Yeah, exactly. In order to save the human programmer time, there's a lot more features built into Python, more functions, more automatic management of memory, and so forth. And you have to pay a price. Like someone else's code is doing all of that work for you. But if they've written some number of lines of code, those are just more lines of code that need to be executed for you. Whereas here, the computer is, at the risk of oversimplifying, only running my lines of code. So there's just less overhead. And so this is a perpetual trade-off. Typically, when using a more user-friendly, a more modern language, one of the prices you might pay is performance. Now, there's a lot of smart computer scientists in the world, though, trying to push back on those same trade-offs. And so these interpreters, like the command I wrote Python, technically can, especially if you run a program again and again, they can actually sort of secretly behind the scenes compile your code for you down to zeros and ones. And then the second, the third, the fourth time you run that program, it might very well be faster. So this is a bit of a head fake here in that I'm running them once and only once, but we could get benefit over time if we kept running the Python version again and again and perhaps fine-tune the performance. But in general, there's going to be this trade-off. Now, would you rather spend the 60 seconds I wrote implementing a spell checker or the 6 hours, 16 hours you might be or have spent implementing the same in C? You know, probably not. For productivity's sake, this is why we have these additional languages. Just for fun, let me flip over to another screen here and open up a version of Python that's actually on in just a second, on my own Mac instead of the cloud so that I can actually do something with graphics. So here I just have a black and white terminal window on my very own Mac, and I've pre-installed Python just like we've done so for VS Code in the cloud for you. Notice that I've got this photo of perhaps one of your favorite TV shows here with the cast of The Office. Notice all of the faces in this image here. And let me propose that we try to find one face in the crowd, sort of CSI style, whereby we want to find perhaps the Scranton Strangler, so to speak. And so here is an example of this guy's face. Now, how do we go about finding this specific face in the crowd? Well, our human eyes obviously can pluck him out, especially if you're familiar with the show. But let me go ahead and do this instead. Let me go ahead and propose that we run code that I already wrote in advance here. This is a Python program with more lines of code that we won't dwell on for today, but it's meant to motivate what we can do from a pillow library, implying a Python image library. I want to import some type of information called some feature called image, so that I can manipulate images, not unlike our own problem set 4. And this is kind of powerful. In Python, you can just import face recognition as a library that someone else wrote. From there, I'm going to create a variable called image. I'm going to use this face recognition's library's load image file function. It's a little verbose, but it's similar in spirit to fopen. And I'm going to open office.jpg. I'm going to then declare a second variable called face locations, plural, because what I'm expecting to get back, per the documentation for this library, is a list of all of the faces locations that are detected. All right, then I'm going to iterate over each of those faces using a for loop that we'll see in more detail. I'm going to then infer what the top, right, bottom, and left corners are of that face. And then what I'm going to do here is show that face alone if I've detected the face in question. So let me go ahead here and run detect.py. And we'll see not just the one face we're looking for, but if I run python of detect.py, it's going to do all of the analysis. I'll see a big opening here now of all of the faces that were detected in this here program. OK, some better than others, I guess, if you zoom in on catching someone, typical Angela. If you now want to find that one face, I think we need to train the software a bit more. So let me actually open up a second program called recognize that's got more going on. But let me, with a wave of a hand, point out that I'm now loading not only the office.jpg, but also toby.jpg to sort of train the algorithm to find that specific face. And so now, if I run this second version, recognize.py, with Python of recognize.py, hold my breath for just a moment. It's analyzing presumably all of the faces. You see the same original photo, but do you see one such face highlighted here? This version of the code found Toby, highlighted him with this green, and voila, we have face recognition. So for better or for worse, this is what's happening increasingly societally nowadays. And honestly, even though I didn't write the code live, because it's a good dozen or more lines of code, it's not terribly many. And literally all the authorities, all we have to do is import face recognition, and voila, you have access. Like, these technologies are here already. But let's consider for just a moment, how did we find Toby? Like, how might that library, even though we're not going to look at its implementation details, how does it find Toby and distinguish him from all of these other faces in the crowd? What might it be doing intuitively? Think back even to pset 4, like what you yourselves have access to data-wise. Yeah? Mm-hmm. Yeah, exactly. And to summarize for camera here, we have trained the software, if you will, by giving it a photo of Toby's face. So by looking for the same or really similar pixels, especially if it's a slightly different image of Toby, we can perhaps identify him in the crowd. And what really is a human face? Well, at the end of the day, the computer only knows it as a pattern of bits, or really at a higher level, a pattern of pixels. So maybe a human face is perhaps best defined in general as like 2 eyes and a nose and a mouth, that even though all of us look similar structurally, odds are the measurement between the eyes and the nose and the width of the mouth, the skin tone, and all of these other physical characteristics are patterns that software could perhaps detect and then look sort of statistically through the image, looking for the closest possible match to these various measurements, shapes, colors, and sizes, and the like. And indeed, that might be the intuition, but what's powerful here again is just how easy and readily available this technology now is. All right, so with that said, let's propose to consider what more we can do with Python itself, get back to the fundamentals so that you yourselves can start to implement something along those same lines. So besides having access to things like a getString function, the CS50 library provides a few other things as well. Namely, in C, we had these. But in Python, we're going to have fewer. In Python, our library short term is going to give you not only getString, but also getInt and getFloat. Why? It's actually just kind of annoying, as we'll soon see, to get back an integer or a float from a user and just make sure that it's an int and a float and not like a word like cat or dog or some string that's not actually a number. Well, we can import not just the specific function getString, but we can actually import all of these functions one at a time like this, as we'll soon see. Or you can even in Python import specific functions from a file. One of you asked a while back, when you include something like CS50.h or standardio.h, you're actually getting all of the code in that file, which potentially can add bulk to your own program or time. In this case, when you import specific functions from Python, you can be a little more narrowly precise as to what it is you want to have access to.